thanks to the organizers for inviting me. And so they tell me that the first talk of the day is usually has to be a good talk so that people will show up. So clearly, maybe I talk isn't all that great. Well, so I'm here to talk about lower level verification for cryptographic software. So I'm going to tell you about two examples. The first is one that I was partly involved in, like multiplication in one record setting curve 25590 implementation. Actually had a mistake in that a carry was added to the wrong bin in a chain. The other is that the squaring routine in 4QLib actually interposed a flag unfracting instruction before the end with carry. So these are two of the fastest elliptic curve libraries around. So to tell you how verification affects this, the curve 25519 bug was offered to verification people as a test, and it was found in half a day using satisfiably modular theory, which means subsolvers, and the bug was found. The 4QLib bug was found during a search for misplaced carries during the course of this work. So verification does make a difference in the correctness of cryptographic software. So what's verification? Verification is a study of showing how something works as designed. So this is a worst case discipline by design. It's trying to show that everything works even in the worst possible circumstances. And typically, it's carried out with things like proof assistance. The most well-known is COC. SA SAT solvers like Minisat, and specifically designed tools that you homebrew. In our cases, we use SAT solvers and some homebrew tools. I don't need to tell you that cryptography is important. The thing that you want to remember is that cryptography, like verification, is a worst-case scenario discipline. You discuss and think about the worst case because there is an adversary trying to take advantage of you. So here's where our tool comes in. In ECC and other cryptographic contracts, typically there's a large field involved. A large arithmetic contract involved. So there is a very large modulus in RSA, and in this P256 and curve 25519, which must be the most commonly used two curves in ECC, there's a large field. And our instruction set only supports 64-bit integers, so this makes everything more complicated. So the thing is that not only is this complicated, people write this in assembly language for best performance. We can see this in OpenSSL and Bo-Yin SSL and 4 other SSLs. And not that many programmers are good cryptographers, and not that many cryptographers are good programmers. So we have a problem in many situations. So here's our thema. Verification and cryptography go together because it's exactly the kind of things which verification should be used for. It's critical, complex, highly visible, and indispensable. And people actually, like computer scientists who doesn't know any cryptography actually know something about OpenSSL. I mean, they know that this is important. All right. So here's the challenges facing us. The verification of nonlinear computation is hard. So for linear computations, SAT solvers can solve a lot of equations and variables in a hurry. I mean, so things that are mostly linear are not a problem for verification. It's the highly nonlinear things like integer multiplication that poses a problem. And we need to prove that's correct for all inputs. And not only that, an algorithm is not implemented just once, it's implemented many, many times. So for example, we use ECC, and some of the time we use a curve like P256, and some of the time we use curve 2/19, and they have different moduli, and the numbers are different and reductions are different, and each instantiation must be verified. And not only is each instance different CPUs and even different programs runs things differently. So there are 40 different assembly routines in OpenSSL for curve 2/19. For the P256 curve. So all this is to tell you that this is a very complex situation, and we need to verify all implementations. So here is our theme. We need to be able to use this, and it must take not a trained individual. So to prove everything in calc is not an ideal situation. It must be something that someone with a very minimum of training can use and can do that quickly. So there are some related work already. There is Fiat. This is a C program synthesize tool that promises to give you the correct C implementation. So if you trust your C compiler, the result will be correct. But can you really trust that compiler? There's Jasmine, which is a portable assembly language with foremost semantics. This means that you have to use calc to prove things after you run Jasmine. There's Hako and there's Bayo, and none of them really addresses our point, which is that we must be able to verify low-level cryptographic software and do it without being a trained individual. All right, so 4 years ago, we tried to verify these assembly programs by using bit blasting. So we reduce everything to bits and use the SAS solver. So in 2014, we used Bootlector, and to verify the academic implementation of X25519. And to verify the modular multiplication, it took 4 days without annotations for 5 hours with a lot of manual annotations. So these annotations also take a trained individual, like actually a very highly capable postdoc to do this. And we also need to do a mathematical simple proof in calc. So this takes a long time. And this is 100 assembly instructions in 4 days. And this is perhaps better than using proof assistance all the way, but this is still not very useful. So this is something that you will use when you finally release your program. So when you are ready to release, you verify it once and hope that it's good, and then you can rest that it's okay. But if you modify your program, you have to do this again. It's another 4 days. So the next year, we see the GF-Berry project by Dan Bernstein down there and Peter Shibaba. And the tool verifies algebraic properties and range properties using a computer algebra system. Actually, no, they verify the algebraic properties using a computer algebra system, and they use the specific range checker for range properties. And that sounds like a reasonable approach, and goes into the question, the approach of using such solvers to solve algebraic problems. So clearly, the GF-Berry project has a good idea. So last year, we extended the idea of GF-Berry to assembly programs and certified algebraic results with calc. The problem is that there's two parts to this problem. There's algebraic properties and there's range properties. The range properties we are checking with such solvers, which is not very hard, but we cannot certify them. To be able to certify them, that would mean that P is equal to co-MP, and that's probably not going to happen. So our tool verifies the same academic implementation of 25519 in 1.5 minutes with no annotation. So the modular multiplication is much easier, and academic implementation takes about 5.5 days. So this is the real Montgomery ladder step that's used in elliptic curve point operations, and in a modified form becomes like Bo-Yin SSL. So this is useful. Again, it's suitable for your production release and not for your daily development. It's not an industrial implementation, and we translated it from Kazan, that's normal assembly language. So not that many projects uses Kazan. So we need more work, and we did more work. So we further optimized our tool, and we verified industrial optimizations in OpenSSL and Bo-Yin SSL. We verified the OpenSSL multi-precision Montgomery modular multiplication for RSA up to 1024 bits. And we also verified the NIST P56 Montgomery multiplication and the Bo-Yin SSL Montgomery ladder step for X25519. Our tool is not certified. The reason is that we don't have the manpower to do that, and also, we believe that this is already very useful when your daily development is concerned. Okay, so we produce a tool chain which we call crypto line. So it has 3 parts. There's a modeling language for cryptographic assembly programs. There's a specification language for functional properties, and there's the verification algorithm. We also provide a tool chain to extract assembly programs from execution using GDB, and we translate assembly programs into the modeling language. And the tool chain makes it possible for somebody who is untrained to produce verification quickly. And this is, I think, essential for adoption. We are hoping to release the tool in a few months so that people can experiment with it if they want. All right. So what's the crypto line modeling language? We have instructions which correlates to things that happen in typical cryptographic assembly software. So there's add with carry. There's subtract with carry. And note that there are 2 different forms, because in your typical program, sometimes we know that a carry is 0. And these different forms of the instructions model, in this case, it says that the carry is discarded. Here, it says that the carry is used. And in this particular case, what we do is we verify using a subsolver that the carry is in fact not going to happen. So we can specify in our language whether the carry happens or not. And then there's multiplication. This is a short multiplication, and this is a long multiplication, where a long multiplication happens when you multiply two 64-bit numbers and get a 128-bit result. And this is a short multiplication, which only gives you like a 64-bit result. And we have shifts. We have splits, which split an integer into 2 parts. There's a conditional move, which is important in modern day cryptographic software because we need constant time behavior. And then there is an assert and assume, which enables us to capture things that we know from the cryptographic software. And here, we need to specify each flag explicitly. So missing flags induce under or overflow checks in BB add and BB sub. So this is our little modeling language. There are special instructions that we add for model purposes. So this one is called BB concat shift left. And this one is a split, and this is a conditional move. So we'll see that later, but what this does, the BB concat left shift, has to do with an instruction in assembly called the shift left double. And what it does is it does a rotate of two general purpose registers. And this is a particularly added instruction to formalize that behavior. Okay, so we are not dealing with any branching instructions for the moment. We hope to add it because rounding time is a side channel. Typically, there is no branches that we need to consider. Now, you might object. Some cryptographic software do have branches, but that's fine. Those branches are independent of your input. That's why we call it constant time. So we just skip over those branching instructions during our verification. So because cryptographic programs are data independent, we don't use branching instructions here. And finally, the crypto line specific language also allows us to specify a conjunction of range and algebraic properties. So for range properties, we can specify that two things are have an order relation, like greater than or greater or equal to. And there's algebraic properties which specify two things are equal or two things are equal modulo something. And we added some syntactic sugar for common expressions. For example, this one, which is very common here. All right, so the multiplication in 25519 starts out by having the following specification. So each of the inputs is less than 2 to the 52. So this is a 5-lim redundant representation. And there are no specifications in the beginning. And after that, we have a program which runs. And at the end of it, we try to verify that the product is in fact equal to the result. modulo 2 to the 255 minus 19, and the range properties actually hold. So here we have a redundant representation and not a 64-bit lim as you might expect. So what we do is that we verify that starting from this range, the resulting range holds, and starting from this algebraic property, the resulting algebraic property holds, and this one uses singular to check. Singular, I believe, is what also used in Sage, so this is a very common tool. And this one we check with Bo-Lecter. So if this holds and this holds, clearly this must hold, although the converse is not necessarily true. For the most part, our model checking like this works. All right, so to verify range specifications, we translate the program and its range specifications to a formula in the with satisfiability modulo theory, and the formula should be unsatisfiable if the program fulfills its range specifications. So notice that a subsolver typically returns one of three things. One is that it says that your formula is not satisfiable, and in some cases it will certify the answer, but not all of the times. Some of the time it just runs without stopping, and you know that this is not a good result. And sometimes it comes and says it satisfies, which means that in our case, our formula has a bug, our program has a bug, and the subsolver will return the result, which tells you that you have a problem. So this is what we do with Bo-Lecter, and we found that there are different subsolving modules that we can use. In some cases, mini-sub works. In some cases, link works. And in other cases, Edical works. So we use all three. And for some realistic programs, both Bo-Lecter and Z3 fails, so not everything works. All right, so what does CryptoLine do? First, we run Bo-Lecter to make sure that there's no overflow, and then we translate the program and algebraic properties to an ideal membership problem. So we have a set of equations. Every single instruction is an equation. And we have an ideal that's composed of all these equations. So this idea is taken from GF values. And what we want to do is that we want the final result to be in the ideal that's generated by all the equations. If this is true, then we know that the program fulfills the algebraic specification. And what we use is singular. All right, so for example, a typical instruction that, a complex instruction like mul RCX. So what this does is that the new RAX plus 2 to the 64 RDX is the value of RAX times RCX. So this is the resulting equation that we put in. And suppose we want to prove an equality, and we want to show, like, if everything, so this Fj is our input, is our instructions corresponding to equations. And if this induction holds, then we know that g of x equals 0 is going to happen. Okay, so here is how it works. First, we compile your program. make it standalone, we extract the execution trace using a script that we have. So we extract from this point, so this subroutine, for example, ECP list Z256 null on Dory. So this is a key multiplication routine in OpenSSL. And we extract from the A.out, and extract a assembly program file. And we add some x86-64 to cryptoline translation rules. We have some common translation rules ready written for you. And we apply the translation rules to translate everything to cryptoline. And we add pre and post conditions. And finally, we need to tune the cryptoline programs so that it matches the semantics and matches what we know about the crypto program. And finally, we run the tool. So when the tool fails, there is an option to emit the input values, which tells you the result is wrong. So in the case where there is overflow or underflow, the result will tell you what inputs makes the result wrong. So the current requirements are the OCaml package manager, which uses OCaml 2.07.0, and you need to use these packages, LWT, PPX, and num. You need Singular version 4, and we need Bootlector 3 with at least legally Ministat and Endicott. So this can all be done using a stock Ubuntu server install. We've also tried to install on Fedora Linux, and it also kind of works. We have not tried other installations. So we are hoping to get everything working on most Unix implementations. Okay, so the translation rules that we mentioned. So the Python script to bbdsl.py, it translates the assembly language to cryptoline by rules provided by users. So for example, when we see move variable number 1, variable number 2, what we replace it with is bb assign the second variable, the first one. So it translates this move instruction from RBP to RAX into bb assign RAX parentheses bb bar RBP. So there's another rule which translates a add instruction. So we have ADDC carry the second variable bb bar, the first variable bb bar, the second variable. So it adds the first variable to the second variable. So using these rules, we can translate most assembly instructions automatically. And sometimes we need to fine-tune the result. So consider what happens here. We move R8 to RBP, shift left R8 by 32 bits, shift right RBP by 32 bits. What does it do? What it does is it assigns the high 32 bits of OR R8 to the low 32 bits of RBP, and the low 32 bits of OR R8 to the high 32 bits of R8. So we need to translate this one manually, and this is the correct translation. We split RBP and R8, we split the variable R8 into two 32-bit chunks, RBP and R8. And we shift R8 left by 32 bits and call the result the new R8. And that's the correct translation here, and that's what we used in the actual Montgomery multiplication. Okay, so this is the evaluation tool of a very common server CPU with a 2.8 gigahertz Broadwell Xeon. And we can see that everything gets verified. The times are in seconds, and the classes are tools, are routines that are specifically written for Broadwell. So Broadwell has ADOX and ADCX instructions, which makes their arithmetic easier. So the 25519 modular multiplication of Montgomery later step took a minute and a half and 5.5 days. And nowadays it took half a minute and less than an hour. So what this means is that you can use this for your daily development. So when you modify your system, when you modify your routine, you can run it again, do the work again, and in half an hour you have a result, and you know whether your modification is correct or not. So more about recent activities. So at the moment, CryptoLine supports computational reasoning and is multi-threaded. So if you have many CPUs, your verification goes with all your CPUs. The Montgomery later step in boarding SSL is verified in 5 minutes rather than 15 minutes. So this is a recent development. We managed to verify again in 5 minutes the 1,000 bit Montgomery modular multiplication. So this is using RSA, and we are hoping that we can get 2,000 bits because that's what most people use this nowadays, even though 1,000 bit RSA is still used in many places. And we are trying to extend our efforts to post-quantum crypto and extending verification to compiler intermediate representation. So maybe you guys know that GCC and Clang don't compile directly to assembly language. It compiles first to an intermediate language that they have called IR, intermediate representation. However, before that, let me remind you that there's lots of post-quantum crypto to be done. There's entity-based ring LWE like Kyber and Newhope. There's non-entity-based ring LWE like N2 and N2 prime. Here, entity means the number theoretic transform, basically a kind of fast Fourier transform. And we have verified the entity and inverse entity modulo 7681 for Kyber, which has 256 leaves. And we are trying to extend the work to Newhope, which is very similar to Kyber. And we are also currently working on extending the result to N2 and N2 prime, which are non-entity-based ring LWE. We believe that this should be doable. We think that this should be relatively easy. There are other post-quantum cryptography. For example, there is multivariates, and operations are in a field in a very small field, like 31, or in a smaller binary field, like 256 or 16. And this should be doable. The coding-based stuff we think should be doable. I mean, the operations are, again, in a small binary field 2 to the 13. And there are super singular isogenies, which we believe should be possible because we have experience from our ECC and RSA work. So we can, we believe that these are possibly things to work on next. Hash-based stuff is not our domain. We only work with like finite fields, basically. Finally, I would like to tell you that we have verification of compiler intermediate representations. The first question you are going to ask is, why don't we just verify the assembly language? First, there's not assembly for every architecture. And finally, and also, for reference implementations, what we want is correctness and clarity, and also for prototyping of algorithms. And the next question is, why do we not verify the C language? The answer is, not many people use CompCert or any other certified compiler. So even though your C code is correct, you don't know that the assembly language and intermediate language is correct. And the compilers that we use every day, which are GCC and Clang, actually make strange modifications to your code. So if we can verify the intermediate representation before the architectural dependent optimizations, we can trust better the program and the result. So here are some strangeness from Clang. So this is real OpenSSL code, and we take this from the GitHub, and this is a stable branch of OpenSSL and the 25519C implementation. So here is the C code. We multiply something by this constant, 121666, and then we cut it to 64 bits and mask it with this particular mask, this mask, which is 51 ones and then zeros. This is the Clang implementation. You do the multiply, you truncate, and you end the result with the following. Notice the difference. Your Clang believes that this is an optimization. We know that this is really not an optimization, but this is something that Clang does. And we know that this gives the right result. We can verify this. So Clang does something strange, and you might say stupid, but it still works. And this is another strange behavior from Clang. We mask G2, where H2 is 128 bits. And we add to G2 the result of H1 shifted by 51 bits to the right. And G3 is the result of adding G3 to G2 shifted to the right by 51 bits. And finally, we mask G2. So we take a look at this Clang output. And we notice that instead of, what it does is it adds the result of the mask. It masks, it adds, it adds again, and it masks again. So it skipped a masking step. I mean, you can figure out that this actually works. And again, this is an optimization done by the Clang compiler. And GCC does similar things to your code. So we are currently working with GCC, having worked only with Cloud before. So what we have done, we identified a subset of crypto line called LLVM crypto line, which is a Cloud IR, which is being used for crypto. We translate LLVM crypto line to crypto line. We add assertions and assumptions as needed, and we can adjust and we verify. So this is almost like a verifying assembly language, except that the language is different. So here's some verification results. Here is the list P224C, and these are the things that we verified in them. Those check signs means that we have modified the program by hand, and this process means that we didn't modify it by hand. So all these programs, which are taken from this C program, all these functions, most of them are verified without having to modify them. And this is the result of this P521. This one is not really used. This one really is used some of the time. And there are situations where, so in all of this, the commands in the code specify the ranges that should be used for input and output. For these three, we can produce errors. And what we believe is that the commentary is wrong. So probably the person who was writing the code put in the wrong ranges in their comments. Otherwise, everything verifies according to the ranges in the comments. So the three unverified programs contain anomalies which we believe is a mistake by the range specification. And you might say, who uses P224? And you will be right. Nobody uses P24. How about P256? And this is something that people do use very often. And we can see that all of this gets verified, and it gets verified very quickly. These key programs, I mean, everything is within 1 minute. And then there's curve 25519, the C reference implementation. And the Montgomery ladder step is verified in about 15 minutes. So this is like real code in real use, and it gets verified in reasonable time. So for the first time, we can verify industrial low-level cryptographic practically. And it only takes like 5 minutes for 1,400 assembly instructions. You can do this. And you can do this again and again. And this uses sub-solving and computer algebra. And we believe that formal verification and practical cryptography is a perfect match. Everybody should try this. And there's lots of new opportunities in high assurance cryptographic software. I should thank my collaborators. Min Cai, who's a postdoc and who actually did, I would say, most of the hard work. My collaborator, Professor Bo-Yin Wang. There's Andy Poryakov from OpenSSL who helped us with a lot of scripting. Jiaxiang Liu and Xiaomu Shi from Shenzhen University. Okay, so I'll take any questions.
what's the current status of vector instructions in the DGDSL converter?
At the moment, what we do is we put in translation rules we put in specialized translation rules. So this is so when we are verifying hyper, the translator translated vector instructions into lots of small scalar instructions, and it sort of worked. I mean, we verified hyper, the entity, yeah.
So do you have like numbers for how many vector instructions are currently supported? Is it reasonably comprehensive? Should any vector program pretty much use it?
At the moment, I'm afraid that you might need to add in some translation rules yourself. So in other words, it's not all comprehensive right now. Just the ones that gets used in hyper and New Hope, which are basically the same.
Question, comments? Thank you for your introduction on the verification of software, query software. But my suggestion is checking the whole verification. I think very difficult now, I guess. It's not all time. It's really difficult to check user search, I guess. The alternatives is a very simple idea, is to use the post-column systems, like dual implementation or multiple implementation, and it will give us some input and then check the output by checking whether it's working ideas. It's much more simple than for the question.
Yeah, I mean, that's one idea. I mean, like, we can consider, but this is, I mean, that's not the scope of this talk. I mean, our talk is talking about trying to check whether something works correctly.